Have you ever looked at a plastic bottle and wondered if you could just turn it back into oil? Well, today we're diving deep into the science of how to do exactly that. We're talking about a powerful process called pyrolysis, and it's all about turning waste plastic back into useful molecules.
So that's the big question, isn't it? We pour so much energy into making these super durable, long-chain molecules. How in the world do you reverse that? How do you take something so solid and complex and just carefully unmake it?
Well, the answer is a process called pyrolysis. Let's break that down, because it sounds complicated, but it's not. Thermal degradation is just a fancy way of saying we're using a ton of heat to break stuff apart. But the real secret sauce, the part that changes everything, is that last bit, in the absence of oxygen. All right, so here's our game plan for this explainer. First, we're going to crack the code on what's really happening at the molecular level. Then we'll find what's called the Goldilocks zone for controlling it all. We'll look at the different engines that make this happen. And finally, we'll get into the products you get and the very real perils involved.
Okay, so let's jump right in. What is actually going on inside that big machine when you heat up plastic without any oxygen around?
Now, the first thing you have to get straight in your head is that this is not burning. Not at all. Burning, or combustion, uses oxygen to completely destroy molecules and release energy. You end up with CO2 and water. Pyrolysis is the total opposite. It's about carefully taking molecules apart, deconstructing them in an oxygen-free zone to get valuable little hydrocarbons back. So picture a plastic polymer, like a super long paper chain. When you heat that chain up past 400 degrees Celsius, it's like a pair of invisible molecular scissors start snipping that chain completely at random. This is called random scission, and it creates this chaotic mess of smaller chains, all in different lengths. And the result of all that chaotic snipping is, well, you can't just get one thing. Physics says so. You always get this trio of products. You get a liquid oil, that's usually the main prize, a solid carbony char, and a flammable gas called syngas. Now, the amounts can change, but you will always get these three. Okay, so if the process is so chaotic and messy, how do engineers actually control it to get more of what they want? Well, it really boils down to mastering two main levers. Lever number one, and it's the big one, is temperature. You can think of 500 degrees Celsius as the Goldilocks zone. If you go too cold, you just end up with this useless, waxy gunk. If you go too hot, you basically shatter the molecules into tiny gas particles and you lose all your valuable liquid. But right around 500 degrees, it's just... The second lever is time, or what engineers call residence time. It's just how long you keep the plastic hot. And this is wild. If you heat it and cool it down super fast, like in less than 2 seconds, you get the most liquid oil. But if you let it cook slowly for hours, you'll get the most solid char instead. The timing completely changes the outcome. So we know the what and the how, but where does all this actually happen? Well, it takes place inside these huge, complex machines we call reactors. And here's the thing you gotta understand. There's no single perfect reactor. It's kind of like vehicles, right? You wouldn't use a Formula One car to haul lumber. Engineers have to pick the right tool for the job, and it's always a trade-off between efficiency and just plain toughness. This table basically lays out the main options, and you can see those trade-offs right away. You've got the rotary kiln, which is a beast. It's tough, but the oil it makes is just okay. Then you have the fluidized bed, which is super precise and gives you great oil, but it's really complex and picky about what you feed it. Let's just zoom in on the rotary kiln for a second. This thing is the workhorse of the industry. Just imagine a giant cement mixer that's being cooked from the outside. Its biggest pro is that it's tough as nails. You can throw big, chunky, messy stuff in there, like whole tires. The con? It's not very good at getting the heat inside, which means you often get less oil out of it. Now, let's look at the complete opposite, the fluidized bed reactor. This thing is the high-tech precision machine. It uses a bed of hot sand that basically acts like a boiling liquid, and it transfers heat incredibly well so you get a lot of high-quality oil. The catch? It's delicate. It needs the plastic to be a uniform, almost powder-like consistency to work. So yeah, no whole tires in here. All right, so we've covered what it is, how you control it, and where it happens. But what about making the process even better? And maybe more importantly, how do you manage the very serious dangers that come with it? One way to seriously upgrade the output is with something called catalytic pyrolysis. This is where you add a special material, a catalyst, into the reactor.
Remember our molecular scissors snipping randomly? Well, a catalyst is like giving those scissors a guide. It steers the reaction, forcing the molecules to break in very specific ways to create more valuable products.
I mean, that sounds amazing, right? A way to take a chaotic process and make it precise. So what's the catch? There's always a catch. And the catch can be summed up in one very frustrating word: coking. Those tiny little pores in the catalyst that do all the hard work, they get completely clogged with carbon in minutes. The catalyst becomes useless, so you have to constantly pull it out and clean it in this really complex and expensive process. It really is the Achilles heel of this whole advanced technique. And this brings us to a really critical reality check. A pyrolysis plant is not a fancy recycling center. It is a chemical plant. You're dealing with a chemical process at incredibly high temperatures with flammable materials, and it demands the exact same level of serious engineering and safety as an oil refinery. And the risks are no joke. That syngas we talked about, it's highly explosive. The liquid oil can contain carcinogens like benzene. The hot char can literally burst into flames if it touches the air. And, of course, any leak in the system could be catastrophic. Managing all of this is absolutely crucial. Which really brings us to the final thought here. The technology to unmake plastic is incredibly powerful, but it's also really complex and comes with some serious inherent dangers. It offers this fascinating potential solution to our massive waste problem, but it also forces us to ask a really tough question. Is this the most sustainable way forward? That's something to think about.